Hello, in this video we look at the rotation of axes. So here we have an equation x squared plus xy plus y squared equals to 1. And to the left of the equation we see that the graph of it looks very much like a ellipse, and it's rotated based on what I can tell about 45 degrees. And actually we'll go ahead and state that the angle that we'll rotate the x and y axes is going to be 45 degrees. Now, in actuality, if you really did want to look at, say, for example, how to get the angle, you can actually base it off of the equation ax squared plus bxy plus um, cy squared. And this would be still, say for example, um, plus dx plus ey, and then plus f, and this equals to 0. Now, basically there are ways to tell if this is a parabola, ellipse, or a hyperbola, for example. Now, you'll notice that some of the terms actually are missing, and that's okay, because actually that's going to help us in terms of like being able to classify this actually as a particular conic that you would be familiar with. So for this one, for instance, we can actually just use that the product of A and C, because it's positive, it's actually going to be a an ellipse actually. So here you have that A equals to 1 and C equals to 1. But that means that A times C is going to be greater than 0. So in actuality, when we have that this product is greater than 0, this will indicate that we have an ellipse. So essentially we already know that it is in fact an ellipse. But more specifically, the other way that we could tell that this is an ellipse, for example, is if we look at the discriminant of b squared minus 4, and we'll write it like this, ac, and we'll say that if this is less than 0, then similarly it's going to lead us to the same conclusion that you have an ellipse. So notice that 1 squared minus 4 times 1 times, well, 1 is going to be equal to negative 3, which is less than 0. This indicates, sure enough, that we do have, in fact, an ellipse. Okay, so either way, there's two ways that we can just look at this and determine that this is, in fact, an ellipse. Now, the way of which that we would actually determine like what does this look like in a different coordinate system, because we're used to the x and y plane. Okay, like that's x, that's y. But if we look at it carefully, we can see that perhaps there's a different coordinate system that builds upon an xy prime, so x prime, and y prime. Okay, now for this, we actually do need a few things in actuality. We need specifically that what the angle would be if we were to rotate it, and what would x and y be equal to. So for this one, we're going to say that x is equal to x prime cosine theta minus y prime sine theta. Now, with the y is going to be equal to x prime sine theta plus y prime cosine theta. So now we choose a theta value. And in actuality, we do have that there is a way to determine specifically like what would theta have to be, okay? And in actuality, if you would like to know what that is, well, the method that you would determine what theta is by using that cotangent of 2 theta equals to a minus c divided by b. Now, in any case, if you look at this carefully, you'll realize that the theta can be restricted from 0 to 2, well, from 0 to pi actually. Because if you rotate the axes more than that, then you're just kind of back to where you started in actuality. So that we should be mindful of in any case. So here, we're going to say, well, we're going to choose. And we're going to say let theta equal to 45 degrees. Now keep in mind that if you did plug this in to this equation, you would see that the equality would hold. Or, 1 minus 1 is 0, and cotangent 2 theta equals to 0 is only where 2 theta is equal to 90 degrees, which in any case you have is 45 degrees. So same thing. Okay, so x is equal to, well, x prime cosine of 45 degrees minus y prime sine of 45 degrees. But this is going to be basically x prime root 2 over 2 minus y prime root 2 over 2, okay? Because, yeah, sine of 45 degrees, that is from our 1, 1, root 2 triangle, or the 4590 triangle, okay? Now, with respect to the x prime, or the y, so y equals to x prime, but that's basically the same thing, isn't it? Like just square rooted 2, and then plus y prime, and that's going to be square root of 2 over 2. Okay, now notice this. This is going to be basically root 2 over 2 times x prime minus y prime. But then this, you can just rewrite that as root 2 over 2 and then times x prime plus y prime. Okay. Now, notice that we do have to square this, right? So in terms of x prime squared, well, that's going to be root 2 over 2, which in any case is equal to a half when you square it, okay? And then when you square this right over here, you should get x prime squared minus 2x prime y prime, and then this is going to be plus y prime squared. Okay. Now, similarly, y prime, actually, I'm sorry, this should be x, yeah. This should be x squared, yeah, because you're squaring that. So that should be this portion squared, which is just 1/2, and then this gets squared, but that's this one right there, yeah. Okay, so that means that this one over here, the xy squared equals to basically the same thing essentially, because you have that it's a perfect square trinomial, and those are basically perfect squares, right? Okay, so here, what we could do from here is also look at what is the product of x and y. Because one thing though, and maybe, yeah, we can scroll up a little, why not? Okay, so let's scroll up a little bit, and let's go ahead and add these two, because accordingly, we're going to add these two. So x squared plus y squared is equal to, well, notice that here you're going to have 1/2 times x squared minus 2x prime squared minus 2x prime y prime plus 2, well, actually it's y prime squared, and this is going to be plus 1/2 times x prime squared plus 2xy. And these are primes. Okay, now, when you simplify this, you're going to have to distribute and then add respectively. But if you do that, hopefully you'll see that when you take 1/2 of the first term, that plus the other, it's just going to be x prime squared. But then notice that you're going to end up with basically minus x prime y prime. So that's going to be minus x prime y prime plus y prime, and that's going to be squared. Now what I didn't do was this one over here, but that means that they're basically going to cancel each other out because one is positive and one is negative. So we have that when we combine these two, that cancels out and that cancels out, which is actually the basis for when we do this expression, or when we use this expression over here, that we need basically anything with an x prime, y prime to cancel out in any case, because we want to be able to tell specifically what this conic is. Okay. Now, moving forward, I think that what we do need to do is actually just say that this portion over here is x prime plus, well, it should be x prime squared plus y prime squared. Okay. Now, for the x and y, it's going to look like this. You're going to have xy is equal to, well, basically, you know that you're going to take essentially these two, and you're going to multiply those two. So that's going to be equal to, essentially, you have root 2 over root 2 multiplied by x prime minus y prime multiplied by root 2 over root 2 x prime plus y prime. And when we move this over, when we multiply it, you should end up with 1/2. And then that's going to be x prime squared minus y prime squared. Okay, now, if we go ahead and we look at this even further, what we need to do is to go ahead and add. So we're going to go ahead and add, and this is going to give us basically, yeah, so we want to add, right? So we want to add, and this was it +1? It's +1 perhaps. Yeah, +1. So here's what's going to happen. We're going to distribute this, right? And we're going to add it to this over here. So far, we have x squared plus xy plus y squared equals to, so we've already combined basically the x squared and the y squared, and essentially that was where we got the x prime squared plus y prime squared. But notice this, okay, so distribute this, and here's what we're going to have. Plus 1/2 x prime squared minus y prime squared. So that should be minus 1/2, right? Yeah, so minus 1/2 actually. Okay, so here what's going to happen is that this is going to get added to 3/2. So you have 3/2 x prime squared, and this is going to be minus y prime and this is going to be divided by 2, because we have that that's divided by 2, but remember that all of this was equal to 1. Ah, it should be plus, right? Yeah. So it should be plus. Okay, so we have that that should be plus, and now it looks that we have essentially a hyperbola based on, not hyperbola, I'm sorry. This is an ellipse. Okay, so this is an ellipse, and this is root 2. Now, the thing though is that when we rewrote it, here's what we have. We have that this is going to be x prime squared divided by, well, in reality, that's just really just 2/3, right? Okay, so that's 2/3, and this is plus y prime divided by 2, and that's equal to 1. Okay, so essentially we have here that one of these is equal to, well, a greater number, if that makes sense. So here we have that this is going to be 2/3, and that's the square root. But of course, that's going to be the square root of 6 over 3. Okay, so here we have the square root of 6 divided by 3, and then we have also the square root of 2. Okay, so here, let's basically find that the square root of 6 and divide this by 3. Okay, so this is clearly going to be the smaller one. So here we have the a is equal to root 6 over 3, and that the, well, no, this is the b, right? Yeah. And this is the a. Okay. So here you can probably find then c from this, because this is going to be basically that c is equal to the square root of 2 minus 2/3, of which in this case is going to be 4. So 4 over 3, and you take the square root of that. But when you do this, you end up with 2 over root 3, which is equal to 2/3 root 3. So here we know what a is, and here we know what b is. But in this case, we know what c is as well. Okay, so essentially the conclusion to this is that we end up with basically a vertical ellipse, and essentially from there we're just going to say that the center, because it's at 0, that it's going to be at 0 2/3 root 3 from the center, that is, okay? And then of course we know that one of the vertices is at 0 root 2, and then at 0 negative root 2. Now if we wanted to find the asymptotes for this one, well, this one doesn't have any actually, but you at least know what the major axis is, and it's the vertical axis. But if we go back over here, where we have this right here, we can tell that this definitely is, in fact, a ellipse that was rotated basically 45 degrees in terms of a vertical ellipse in any case. And, we could actually just plug in what we found, for example, because we know that we can actually just go ahead and just say, well, that was divided by 2/3, and this was divided by 2. So here we have that that was the vertex, right? And this was the vertex as well. But notice this, that here is the co-vertex. So here is the co-vertex. And it could be that, it's just the scale that we have here in this case, that we're not really seeing the same thing necessarily, but it basically would be the same thing either way, because you have that when we converted it, we see that basically that, yeah, that this definitely is in fact our equation now in any case. Why it looks a little different, that's just because of the change of coordinates in any case in terms of the axes that we do. But strangely enough, if you were to plug in the vertex, because you now know that, for example, that one of the vertices is at 0, root 2, but notice that that is x prime and that is y prime, meaning that you could actually find like what is the vertex in any case, like if you plugged it back in. Okay, so in this case, that would imply that one of the vertices is at, let's see, 0 and -1, and then another would be at 0 and +1. Let's see. Because we said that the vertex was there. So, let me see. Okay. So at 0, that's 1, and that's another. But, so the thing about this is that, yeah, if you know that this is going to be the 0 and the 2, and you go back in terms of the x and y coordinate system, you plug this in and you're going to get that that's going to be -1. Okay, so that makes sense that if you plug in 0 and root 2 into what x was, which was the x prime cosine theta, you get -1. But if you look at the y variable was x times sine plus y prime cosine theta. But basically, if you use that same value, well, in this case, you're going to get +1. So that means that the vertex is at -1, 1. So for this, if we go back to the graph of the equation, we have that this would be -1, and then looking at this carefully, 1 negative, -1, -1, yeah, it's right over here actually, no, -1, -1, there you go, there it is. So here we have the vertex at -1, 1. It's hard to see with this, but we can see that, yeah, that's -1, 1, which means that the other vertex has to be basically at 1, -1. So then, right, so here we're kind of close to here, where we can see that that's going to be 1, -1. Okay. So in any case, we can actually convert any equation into the same form that we're familiar with, and then go from there in actuality. But the thing that was kind of interesting was if we use this original equation and we plot it in the x and y plane, then you'll see that it's almost circular actually. But then when you look at it in the original, it's an ellipse just rotated, which I think is kind of interesting actually, but it could be just the scale probably.